Good morning. I'm Professor Poornima of the Department of Systems Design and Engineering. As courtesy to our continuing acknowledgement of territory, I'm going to read the notice. The University of Waterloo acknowledges that much of our work takes place on the traditional territory of the neutral Anishinaabe and Haudenosaunee people. Our main campus is situated on the Poornima tract, the land granted to the Six Nations that includes 6 miles on each side of the Grand River. Our active work towards reconciliation takes place across our campuses through research, learning, teaching, and community building, and is centralized within our Indigenous Educative Office. We are here to hear Dr. Poornima Unnikrishnan, who is a postdoctoral fellow working with Professor Kare at the Electrical and Computer Engineering, and myself at the Systems Design Engineering. She's a hydrologist with PhD from Indian Institute of Bombay, the city of Mumbai, India. She has planned at least 2 talks in this series, and the first one today is being presented for introducing the research area of moisture tracking, atmospheric moisture tracking, and why it's a very timely topic now. I invite Dr. Unnikrishnan to give us.
Good morning, everyone. Thank you for the introduction. So as mentioned, this is the first of the 2 series presentation that we will be delivering on the topic of atmospheric moisture tracking. As this atmospheric moisture tracking is a relatively new research domain, in this presentation, I'll be giving a brief overview of the research domain, atmospheric moisture tracking, and a brief review of some of the work that has been going in this research domain. So as an outline, so as I said, I'll be giving a brief introduction of the atmospheric moisture tracking procedure and some terms that are related to this atmospheric moisture tracking and some of the applications of doing this research. And finally, the research objectives of my in this research domain. I'll be explaining this in this presentation. So let's start with the hydrological cycle. As we all know, hydrological cycle depicts the flow of water in the hydrosphere. So this shows the atmospheric part of this hydrological cycle is the topic of interest in this presentation. So in this figure is adopted from a book published in 1988. In that study, it was estimated that 40% of the precipitation that is occurring on land is due to the evaporation from land, and 39% of the precipitation on land is due to the evaporation from ocean. So, but recently there has been a lot of interest in understanding the atmospheric transfer of moisture and in quantifying the ratio of contribution of continental and oceanic evaporation into the precipitation. And many researchers recently have, recent studies showed a different picture of this ratio. Recent studies showed that 40% of the precipitation on land is due to the evaporation from land, and 60% is due to the evaporation from ocean. So as this atmospheric moisture tracking and these models are relatively a new area of research, and since there is the discrepancy in the different studies, then there is a need to study this atmospheric moisture tracking in detail and to identify the source of these discrepancies. So the major questions that need to be addressed and that need to be answered in this research domain are given below. The first and most important research question is, where is the source of precipitation? If we are considering a specific region, so where is the source of precipitation of that region? And the second question is, what happens to the water mass after it gets evaporated? And most important and pertinent and actually needed to address more is how these moisture sources are affected by the change in land use and climate change scenarios. Currently, recently, researchers are more interested in addressing, in finding out different methods and models in addressing these questions. So atmospheric moisture recycling. It is the process of the flow of atmospheric moisture from evaporation till it gets precipitated. So it is the atmospheric moisture tracking is the process of following the path of moisture through the atmosphere. Once it gets evaporated, it gets precipitated, tracking where and how much amount of this evaporated water is getting precipitated. So finding out the source and sink region of precipitation and evaporation is the major concept of this atmospheric moisture tracking. So an important aspect or concept on doing this atmospheric moisture tracking is residence time of global atmospheric moisture. So it is the average duration in which the water molecule stays in the atmosphere after it gets evaporated. So this is important because we are modeling this, we are tracking the atmospheric moisture. So the average residence time of global moisture content is important, and the researchers have identified that the global average residence time is around 8 to 10 days. This is the global average value. This can differ based on the region. And it is also important to note that even though the total volume of global volume of water in the hydrological cycle remains almost constant, the distribution of this water is continuously changing in time and in the space. Like the distribution is continuously changing on continents and regions and different local drainage basins. So there is a need to address moisture tracking, and we need to address the hydrological cycle in a more regional way. So another important concept in this research domain is atmospheric moisture watersheds that was introduced by Case et al. In 2012. That is a useful concept in explaining the results of atmospheric moisture tracking. So these are two watersheds, atmospheric watersheds known as precipitation shed and evaporation shed. So as we can, this first figure is the conceptual framework of precipitation shed. Precipitation shed is the area that contributes evaporation to a specific location precipitation. That means if we can see this figure, so if we are considering this sink region shown in this small box, so this the area that contributes evaporation for this sink region's precipitation, the entire area is called as precipitation shed. So similarly, the evaporation shed is the area that receives precipitation from a specific location, evaporation. So if we are considering the source region, so where all this water vapor that is evaporated from the source region is transported and where all it is precipitated. So that entire region that receives precipitation from this location is the evaporation shed of this specific location. So this concept of atmospheric moisture tracking is essentially helpful in explaining the and in finding out the land use changes and climate change scenario of an evaporating shed or precipitation shed and how it is affecting the specific location. So the precipitation recycling ratio is another majorly used measure in atmospheric moisture tracking. It is the contribution of the region's evaporation to its own precipitation. So if we can take a look into this image, that can be clearly understood. That is, the precipitation of a region can be classified into two components. One is due to the precipitation that is due to the evaporation that is advected from out of the region, and also from the evaporated water within the region. So here, this is the P is the total precipitation, and PA is the precipitation due to the evaporation that have been advected from out of the region, and ER is the evaporation that is within the region that is contributing as precipitation within the region. So PR is the regional precipitation due to the evaporation in this region itself, and the ratio of PR to regional precipitation to total precipitation will give the relative contribution of a region's evaporation into its own precipitation. So this is a majorly used measure in identifying the relative contribution of the region's evaporation. But we have to also note that this ratio, this measure is highly dependent on the size and shape of the region. So if we consider a narrow strip of land, then if we want to calculate this precipitation recycling ratio, then it can go close to zero, because most of the the precipitation that is happening in that region could be due to the evaporation that has been advected from out of the region, because the region is too narrow, and the evaporation that is happening within the region can also go out of the region due to the width of the region. So this measure is highly dependent on size and shape of the region. Hence, a new measure, a comparatively new measure of precipitation for identifying the contribution of the continental and oceanic evaporation into a region's precipitation. A new measure, that is continental and oceanic recycling ratio, were introduced by WaterTalk in 2014. This continental recycling ratio is the relative contribution of continental precipitation over the total precipitation. So in here, the total precipitation in a region is classified into two components. One is due to the precipitation of continental origin and precipitation of oceanic origin. Precipitation of continental origin means the precipitation due to an evaporation that is occurring in the land mass, and precipitation of oceanic origin is the precipitation that is occurring due to the evaporation from an ocean. So this ratio of the continental precipitation to the total precipitation will give the relative significance of continental evaporation into that region's precipitation. So, and this is not a specific or dependent on the shape and size of the region. And similarly, there is continental evaporation recycling ratio, which is again the relative contribution of the terrestrial evaporation that contributes to a continental precipitation. That is the terrestrial evaporation that will precipitate as in a land mass than in ocean. So that ratio of terrestrial evaporation that returns as continental precipitation to the total evaporation is the continental evaporation recycling ratio. These two ratios, these two measures shows the relative significance of the continental evaporation on the continental precipitation. So different models that are available for this atmospheric moisture tracking are analytical models, online water vapor tracers, physical water vapor tracers. Out of these, the most widely used or widely accepted method is analytical model, wherein the using the water balance equation, the moisture tracking is carried out. And there are Eulerian water tracking models and Lagrangian water tracking models based on the representation of the space in that model. And it is widely accepted method of doing atmospheric moisture tracking. And as it can be used for forward tracking as well as backward tracking. So let me explain what is forward tracking and backward tracking. Forward tracking is tracking the flow of moisture from evaporation to precipitation. So that is identifying the sink region of evaporation, whereas backward tracing is tracking the moisture source of precipitation. That is, we are tracking from precipitation to evaporation. Both these are available in analytical models. And also it is computationally less expensive compared to the other models. So in online water vapor traces is another method that is available for doing this atmospheric moisture tracking, wherein online modeling on global atmospheric global circulation models are carried out, and the water vapor is the water vapor is tracked from evaporation to the wet till it gets precipitated. It cannot be used for backward tracking. It can only be used to identify the sink region of evaporation. And it is highly computationally extensive model. And the third available method is using physical water vapor traces by means of isotopes. This is by identifying the ratio of stable isotopes available in the precipitation to identify the possible regions of evaporation. But this method is also not very widely used because of the data availability about the isotopes is not much wider. And also we can only get a vague representation of the source of precipitation from this method. We cannot get a more detailed spatial pattern of this evaporation shed from using this method. So the most widely used and accepted models are these analytical models in atmospheric moisture tracking. So water balance is the basic framework for this analytical models, wherein the change in atmospheric moisture storage is related to the horizontal and well as the vertical flux, water vapor flux values, and by analyzing and by solving this water balance equation, this analytical models track the atmospheric moisture to the space. So as I have mentioned, in analytical models, there are majorly two frameworks that are Eulerian-based analytical models and Lagrangian-based analytical models. The difference is in the representation of space. In Eulerian model, the space is represented as grids, whereas in Lagrangian model, it is trajectory-based. In Eulerian model, the moisture transport over these boundaries of the grids are calculated at each time step based on the estimated cell-to-cell wind data and precipitation and evaporation. Whereas in Lagrangian model, the individual moisture parcels are identified and they have a location with specific coordinates, and those locations are updated based at each time step based on the point-based wind flow data and evaporation and precipitation. An example for Eulerian model is the water accounting model, two-layer model. And for Lagrangian model, an example is U-track atmospheric moisture model. And while comparing Eulerian and Lagrangian model, the Eulerian model is computationally more simpler, and it can and it is also reported that it can, with relatively good quality of data, it can get good results if we are using this Eulerian models. So as I mentioned, warm two-layer model is an example for the most commonly used Eulerian water atmospheric moisture tracking model. This water accounting model two layers. It is introduced by WaterTalk in 2014 as an update for the warm one-layer model. Here, it tracks both vertical and horizontal flux of water vapor using these two layers. And the forward tracking, that is to map the sink region of evaporated moisture, that is to map the evaporation shed is also possible, and as well as the backward tracking is also possible using this method. And the various parameters or as four things in this model are include the surface pressure, specific humidity, horizontal and vertical winds, water vapor flux, total column of water, and precipitation and evaporation. These are the four things that are given as parameters into this model. And using this model, you can identify the source region and as well source of precipitation if you want to delineate the precipitation shed. And if you want to delineate the evaporation shed, you can also find out the sink region of the evaporated moisture using this model. So one of the major questions that need to be addressed in atmospheric moisture tracking is how this atmospheric moisture tracking or atmospheric moisture recycling will change under different climate change scenarios. So the major question is, how will this climate change alter the location and significance of source regions and the transport of moisture from these toward continental areas in the future? So that is a major research question. And very few works have been reported considering the climate change in the moisture recycling. Most of the works that have been reported are using the past data. So there is a large scope in identifying this for different regions, how the moisture recycling will behave for different climate change scenarios. In 2020, Benedict has analyzed the atmospheric moisture recycling under climate change scenario for Mississippi River Basin. And this figure shows the mean annual moisture transport into the Mississippi River Basin as per the results of Benedict et al. Under present and future conditions. And this figure, this bar chart shows the present and future. PR is present and future. Present and future moisture transport percentage into this Mississippi River Basin. And this is, let's first look into the oceanic, the moisture transport of oceanic origin. There is moisture transport from Pacific Ocean, Gulf of Mexico, and Atlantic Ocean into this Mississippi River Basin. And under present scenario, and by comparing the present and future scenario, by considering the mean annual moisture transport, the oceanic transport from Pacific Ocean doesn't vary much, but it increases slightly in the future. And from the Gulf of Mexico also, by comparing the present and future climate scenario, the moisture sources from Gulf of Mexico in percentage exceed or increases a little bit. And similar is the case for Atlantic Ocean. And while we considering the continental moisture recycling, in Mississippi River Basin, the moisture source of transport is from within the Mississippi Basin is shown in this arrow, and that is coming from the southwest of the basin is depicted by this arrow. So here we can see that the continental moisture transport has the percentage of continental moisture transport that is causing the precipitation in Mississippi River Basin has decreased significantly for the future scenario compared to the present climate change scenario. So what this means for total precipitation is this is mean annual moisture transport scenario that is shown in the figure, but it is by analyzing it in detail, it can be seen that the winter precipitation is more during the future condition than in present. And there is a slightly decrease in summer precipitation in the region in the future. And this relative decline over the contribution of terrestrial areas to precipitation. This continental area is going to contribute to the precipitation in a relatively declined manner in the future that can cause this decreased precipitation in the summer. And as per Bennett et al., in the future, the moisture source contribution to Mississippi Basin from the oceanic origin, which adds the oceanic moisture from Pacific, Gulf of Mexico and Atlantic from 44% to 47%, and the contribution from continental origin decreases from 33% to 27%. So this kind of studies can analyze the effect of climate change on the moisture recycling pattern, and more work in this area can be done for different regions, and it could be of great insight towards the climate change. I understand the climate change pattern in the atmospheric moisture recycling. So another major question that needs to be answered is effect of land use on moisture recycling. So as we all know, the effect of land use pattern changes on evapotranspiration can affect the evapotranspiration from the land origin, and it can significantly affect the rainfall amount caused due to that evapotranspiration. And we can combine this moisture transport modeling with different scenarios of land use to identify what are the changes that in atmospheric moisture recycling that can happen due to this land use pattern changes. Here, a perfect example would be of the Amazon deforestation. The Amazon, which is considered as the lungs for the planet, lungs of the planet, is currently reported to be undergoing a major deforestation or a major kind of land use change. So how this is going to affect the entire globe in terms of the moisture transport and in terms of the rainfall pattern is of significant importance in the current research domain. And so many works are currently being carried out on this aspect. And it is reported that due to the deforestation that is happening in Amazon, or the land use change that is happening in Amazon, there is significant decrease in the evapotranspiration of continental origin, and which can significantly affect the precipitation and the downwind areas of Amazon. So there are a lot of works that are being carried out in this area, and it needs to be the land use change pattern in atmospheric moisture cycle recycling need to be identified in a more detailed manner for different regions. So this kind of study, which will show the impact of land use change on the moisture recycling, can have wide implications to variety of stakeholders, such as for agriculture, for hydropower management, for human consumption, and also it could be vital for political decisions. So water security and water resilience, it is one of the major theme of current researches. So under this current climate change and land use pattern changes, and this water adaptation and sustainability is coming as a major research topic. So here the moisture recycling can be used as a key to promote resilience. So for example, in dry lands, by stabilizing vegetation-driven like hydrological feedback, by understanding the source and sink regions of precipitation and evaporation in the area, then we can use this moisture recycling as a tool for promoting resilience. And also, if we consider rain-fed agricultural systems, so if we know which is the moisture supply regions by carrying out this moisture recycling modeling, then we can manage that moisture supply region for better resilience in rain-fed agricultural systems. So an important example could be the work done by Keith et al. In 2016, where they suggested to adopt vegetation-regulated moisture recycling as an ecosystem service. So it is how this vegetation-regulated moisture is affecting the benefit, which whole area is benefited by this vegetation in a source region. So identifying the benefit region of this vegetation in source region and to better plan in for future how the vegetations or land use changes in the source region can affect the uh, uh, precipitation in the benefit region. So benefit region is basically the evaporation shed of the source region. So where all this precipitation, evaporation from the source region can get precipitated. So how in this figure shows a case study that has been done by Keith et al. In 2016 at Mato Grosso in Brazil. Here Mato Grosso in Brazil is considered as a source region of precipitation. So it is studied how the vegetation changes the moisture monthly in the precipitation in the benefit regions. Benefit regions is the region within the evaporation shed of the Mato Grosso region. So this figure is the mean monthly precipitation for the evaporation shed of Mato Grosso region. In order to identify the vegetation regulated moisture cycling, they have considered two scenarios. One is for the current scenario with the current land use model with the current vegetation. They have done this moisture recycling modeling, and then this blue line shows the mean monthly precipitation with the current vegetation scenario. And a second scenario is a hypothetical scenario of desert scenario. When the vegetation in the Mato Grosso region is completely deserted, what happens to the mean monthly precipitation of the benefit region and their evaporation shed? So what is happening when it is getting deserted and what is the current scenario? This, by comparing this, we can identify the importance of vegetation regulated moisture recycling, and also we can identify the benefit regions from this moisture regulated moisture recycling, and also we can identify the changes due to land use. And here from this graph, it can be seen that the red color is due to the desert, the scenario for desert. And here, by removing the deserted region, by removing the vegetation in the Mato Grosso region, the monthly precipitation in the evaporation shed of the Mato Grosso region has declined significantly. And there is a dip in the dip in the monthly precipitation during the dry season, which that dip is more wide in the deserted scenario than in the undeserted current scenario. So this shows the relative importance of vegetation of a source region to the entire evaporation shed. And this figure also shows the temporal domain of also overlaps with the important sectors that is affected by precipitation, such as the growing season of agricultural rain-fed agriculture systems such as maize, and the reservoir filling period and the grazing period. So this in this work, the main conceptual framework of identifying vegetation-regulated moisture recycling as an ecosystem service was defined, and this can be more there is scope to study this kind of work more to identify the land use, the effect of land use pattern in the source region, how much it is affected in the sink region. So, as I mentioned earlier, the continental precipitation and evaporation recycling ratio for the globe is as studied by this research is given here. And it shows the relative contribution of continental evaporation to a region's precipitation. So here, first figure is the continental precipitation ratio. And this areas where it is red, that shows that it is of high continental precipitation ratio. That means the percentage of precipitation of continental origin is higher than that of oceanic origin. And that means that region is highly dependent on the land use pattern of their corresponding evaporation shed. So they are highly dependent on the land use change. And in the second figure is the continental evaporation recycling ratio. Here also these similar areas are having a red color, which shows that the continental evaporation recycling ratio is high. That means the most of the water that is evaporated from this area is contributed as continental precipitation. So this area's land use is highly important to be maintained for sustainable precipitation in their downwind areas. And if we are considering the North America, there are also the more about 30 to 50% of North America, in North America, 30 to 50% is contributed by continental precipitation. And similarly, 30 to 60% of continental evaporation is of continental origin. Continental evaporation recycling ratio is higher in the range of 0.3 to 0.6 in North America. So here also, the change in land use pattern can have significant impact on the precipitation in the region. The flow of moisture in different regions was studied by Keith et al. In 2017. So this figure shows the flow of moisture in the North America. So here, let me explain the figure first. So this radial arcs shows the landmass in North America. This is blue color represents USA, and red color represents Canada, yellow color represents Mexico, and this black color represents the ocean. So this figure shows the flow of moisture between these different landmass and between the ocean. So there is a flow of moisture from ocean to land flow of moisture, and also land to land flow of moisture. First, we can first consider the flow of moisture from ocean to land. So just consider this. I'm just considering the USA part. So here, this curve is the flow curve, represents the moisture transport between the ocean and USA. So all these flow curves are bidirectional. So, and the width of this arc represents the fraction of rainfall caused due to that moisture transport. So here we are considering USA, more than 60% of moisture is coming from ocean due to this transfer of flow of moisture from ocean. And then there is, if we consider the link between USA and Canada, there is a small input of rainfall in the fraction of rainfall in USA due to the moisture that is transported from Canada. And there is this area represents the moisture that is coming within the US. It is not connected to the landmass of any other country or any other from ocean. It is within the continental landmass of US. So this shows the interconnections between the flow of moisture between different countries. And if we consider the Canada as another example, this more than 50% of moisture is coming from ocean, and some 14% of this moisture is coming from the flow from moisture from US, and some part is coming from other lands, and some of 20%, about 20% of the flow of precipitation in Canada is due to the moisture transport within Canada. So this shows the dependency of different regions in North America over moisture with moisture transport to get the precipitation. So the research interest, my research interest in the research domain would be to find out the source of precipitation in California region, and to moisture tracking, and to apply the research in agriculture that is happening in California, and to identify or to study this moisture tracking under climate change and land use pattern various scenarios. So I'm considering California for my study. So why California? So here we can see that the most of the Canada's fruit imports are from US. More than 42% are from US. And California Central Valley is the most productive agricultural region in the United States, and it is one of the most productive in the world. So we can, by studying this California's moisture pattern and atmospheric moisture recycling pattern, we can actually get a more idea about the agriculture, that is how it is going to affect the agriculture in this region, and eventually it will affect the region in, which supplies the fresh produce from the California. And Central Valley in California is one of the largest irrigated regions in the world. And it is found that when irrigation water is applied, the evapotranspiration can get substantially increased. And in this region of California, it is reported that annual evapotranspiration exceeds annual precipitation by almost 60%. This excess evapotranspiration can be attributed to the irrigation water that is being supplied into this region. And this irrigated water can have effects in the atmospheric moisture recycling pattern also. So to study this effect of human intervention such as irrigation into the atmospheric moisture recycling pattern is of great importance in such a region where the irrigated water is very high. So there has been research done by Lowe in 2013 regarding how the irrigation California Central Valley is affecting the evapotranspiration cycle in the Central Valley and in the nearby state. And this figure shows the regional loop of hydrological cycle due to irrigation in Central Valley. They have found out the difference in the evapotranspiration that is occurring due to irrigation. And it is seen that due to irrigation, the evapotranspiration in Central Valley has increased, and also not only that, the evapotranspiration in the southwestern United States also increased by 8%, and the runoff in this Colorado River Basin also increased by 28%, which there is a precipitation increase in the southwestern US by 15% due to the irrigation that is given in the Central Valley of California. There was no much more precipitation in Central Valley of California due to this evaporation increase, because most of the evapotranspiration was transported over to the southwestern United States, and most of the extra precipitation was happening in the southwestern United States. So this shows the importance of studying the human interventions in this atmospheric moisture recycling, because how the irrigation water affects the atmospheric moisture recycling on an overall manner. And we can identify what all the impact of this kind of human intervention into the atmospheric moisture tracking. So concluding remarks, with the current availability of high quality data, moisture recycling science can be well understood, and we can identify the source and sink regions of different areas, and the land use and climate change scenarios can be integrated into the moisture recycling model to better understand the future scenarios that can happen in the atmospheric moisture recycling. And these kind of research works can have a variety of implications for a variety of stakeholders, such as in agriculture, hydropower, and in human consumption. Research objectives for my upcoming research would be to determine the precipitation shed of California and to analyze the moisture recycling under various climate change and land use changes. And we can, as the California is the most of the agriculture in the US happens in California, we can integrate the yield of fresh produce in California with this moisture tracking models that can help in predicting the yields in California in a much better way. Thank you.
Thank you, Dr. Poornima. I think the questions probably to take the audience here before we look at the online questions if there are any.
Yeah. No, like this is the first part of the thesis presentation. So this was just about giving an introduction and literature review of the research domain. In the next part of the presentation, we will be presenting our research outcomes. Yeah,
Just one second, you have to repeat.
yeah, that's good. The question is, can this study be applied, like the study that I just showed in California, be applied in different regions in Canada to study the effect of irrigation in moisture recycling? Yes, it can be done in different regions. Like you can input the data for that region to identify how it is affecting the downwind area or the nearby area in evapotranspiration and also in precipitation. So it can be done. Sorry, yes. The pressure value is there. In the forcing value of the question is in the forcing parameters in warm two layers. The temperature parameter is absent. So the pressure, there is surface pressure value that is given as forcing that will take care of this temperature. And that this evaporation is there. So evaporation is given as forcing. Yeah, velocity components are there. The horizontal and vertical velocity, wind velocity components are there. That is the major one of them. Yeah, they are the input parameters. They are forcing for this. They basically determine the transport of the water vapor, the specific humidity and the horizontal and vertical water vapor wind velocity. Yes, in this, here in this equation, this first term, it is it determines the horizontal atmospheric moisture storage variations, and it includes the specific this equation that if we want to determine that term, it includes the specific humidity and surface pressure. All those terms will come into that picture in that term. So I'm just showing the basic equation for water balance. It will come in these terms.
Vertical is done only now.
Yeah, vertical is only done lumped because only two-layer data. The model is two-layer. The vertical information is lumped in 2 layers. Driven by, sorry. Yeah. Yeah, they are reanalysis. We can give reanalysis data. So the data most commonly used is ERA incident reanalysis data, but we can give different kinds of data like land. We can change the land use data by different land use area. We can use the climate model data. So most commonly used is area analysis.
Is there any consideration so far in uncertainty in data and parameters?
No, like there have been some references to that, but that has not been done till now, considering the uncertainties in the parameters also in this model. So that is also another major area of research that needs to be explored by considering how this uncertainties in these input parameters will affect this output by maybe by applying the stochastic methods. So That has to be explained. That hasn't been explained. Yeah, I have.
Okay.
Yes.
Yeah. Okay. So yeah, so this is part one, and the part two is where all five.
Yes.
We do have a little.
Sorry.
Yeah, we do have the system or doing the work available. Now is the question of applying it for California region, for at least for the current research that we are doing is important. It's not the only place, but because we're looking at the agricultural yield to support predicting prices in Canada, so we need to know more about how agricultural yield is affected by various much affecting topics. Thank you. Thank you for everyone who came here as well as in online.